Hey, what's up? What's up, YouTube? How's it going? We are going to do another live practice stream, practicing mathematics live on the internet. How are the audio levels this time? I think that everything should be correct. Cool. So, welcome if you're new. My name is John. I am a mathematician turned software engineer turned YouTuber, I guess. I stream my practice sessions in classical guitar, and now I'm streaming my practice sessions in mathematics. So join me on this journey as I go through a crazy midlife crisis and pivot away from a high-paying career in software toward a wonderful, fulfilling, meaningful career teaching mathematics. I am trying to become a high school math teacher, and YouTube is my way of practicing and building up the habit of practicing math every day. So we've been working on linear algebra for a while, and today we're going to be on chapter 6 on orthogonality. Yo, what's up, Ta3575? Thank you for making it. So today we've got orthogonality. We've got a chapter on, we'll be working problems from this lovely book. A problem on projections, a problem on the Gram-Schmidt process, one on orthogonal matrices, and if we get to it, sections 4 and 5, the projection matrix and the method of least squares. We'll see how far we get. But to begin, here's the first problem, and this one should be fairly straightforward. Okay, so my favorite topic, linear algebra or math in general, or projections? Do you like orthogonality in particular? That's cool, if so. Alright, let's put away the classical guitar music. That's my channel, by the way. I have a guitar channel. So, solution to this one. Solution. Find the projection of, let's call this vector v on the span of this one vector, lowercase w. So, the span of... Yo! Hell yeah, dude. Thanks, Leo. Leo Lectures. What's up, man? Good to see you. I will check out that post in just a second here. But for now, let's do some projection problems. All right, so the formula for the projection of v onto another vector w is v dot w divided by w dot w times w. So, v dot w is negative 2 minus 6, negative 8 plus 2, negative 6. So dot product, you multiply the components and then add them together. Got to go to lunch, but thought you might find it fun. I will check that out for sure, dude. Good to see you, Leo. Thanks for saying hi. Okay, so dot product of those, let me double check that. Negative 2, negative 8, yeah, negative 6, that's correct. And then the dot product of w with itself is 4, 13, 14, 18. And then times the vector w, which I will write now as a column vector. 2, negative 3, 1, 2. So this is negative 1/3 of w. So we could write this as negative 2/3, positive 1, negative 1/3, and negative 2/3. You could write it that way, or you could keep the 1/3 factored out, and I think that would look nicer, but, tomato, tomato. Here is our projection vector. Hey, how you doing? I'm doing good, man. What's up, Bloodfire? What's up? Been doing for really a while. Gotta respect the consistency, lol. What did you learn yesterday? Thank you for asking. Yesterday, I learned eigenvectors and eigenvalues. I practiced some problems about eigenvalues, eigenvectors, and I'd say that the one thing that I really learned well yesterday was how to derive matrices for these generating sequences. So if you have like a weighted Fibonacci sequence, if you have a Fibonacci sequence or some sort of weighted Fibonacci sequence like this, how do you write down a matrix that corresponds to that sequence? And then from that matrix, you can do a diagonalization argument. And so I diagonalized that matrix, found the eigenvalue, eigenvectors of that matrix, diagonalized, then you get this formula, and then you can write down like an explicit formula for the kth term. And in this case, if k goes to a large number, then each of those eigenvalues tend to 0. Like lambda to the k tends to 0 because each of those are less than 1, magnitude less than 1. That stuff is beautiful. Isn't it, man? Like, I think that all of this is very beautiful. Eigenvalue eigenvectors are gorgeous. Yeah, we're getting into some really cool, really nice, elegant math. What else did I work yesterday? This one was just like a regular find a characteristic polynomial calculation. And then this other problem was, diagonalization. So not just find the eigenvectors, but also see that you can diagonalize a matrix with the matrices C and D, where one is the column vectors are the eigenvectors, and then the other matrix is D has the eigenvalues along the diagonal. And we confirmed that CD, which is here, 1, 1, 0, 0, 0, 2, also equals AC. So that confirms this diagonalization is accurate. Thanks for asking. Yeah, I should do a better job of like trying to summarize the previous stream at the beginning of the next one. But anyways, yeah. What about you, Bloodfire? What are you studying? What are you working on or studying or whatever? Okay. Let's let W be the span of W1, W2, zero, 1, 0, 1, 1, 1. So I'm just giving labels for those vectors. Then, how do I want to write this? We let B1 equal W1, and then we let B2 equal W2 minus the projection of W2 onto B1. I think that this is correct. I may have gotten that backwards. But no, I believe that this is correct. Okay, so this is W2 is 1, 1, 1. The dot product of W2 and B1, 0, 1, 0. The dot product of W2 and B1 would be 1. the dot product of b1 with itself is 1 times vector b1, 0, 1, 0. I'm using I'm using b to mean an orthonormal basis. I don't know if there's like a good standard notation that implies orthonormal basis, but we want to construct capital B is 2 vectors such that the span of such that B equals W and BI dot B such that B, the span of basis vectors WI equals the span of basis vectors BI and I'll just say B is orthonormal. That's like, so we're aiming to convert W1 to B1, B2. We're close on this. But we haven't normalized necessarily. So this would be the vector 1, 1, 1 minus the vector 0, 1, 0. And now this vector is 1, 0, 1. Next, we normalize. This is what I was just saying. We haven't yet normalized our vectors. So B1 prime is 0, 1, 0 normalized, which is just 0, 1, 0. B2 prime is 1 over the square root of 2 times B2. And I can see that those two vectors are orthonormal, that they're orthogonal. If you take the dot product of those two vectors with each other, the dot product is 0, and both of them are unit vectors. So, I think we're done. And they're linearly independent, and so are the first two. So I think that may not be enough to say that that the spans are equal, but by construction here, we know that the span of the two sets are equal. It's a little hard to describe, sort of. So, this is called the Gram-Schmidt process. I wanted to take a look at my graduate level math book because I know that it mentions the Gram-Schmidt process somewhere, the Gram-Schmidt algorithm, but I don't know if it stated what it is. I think it just says that there is an algorithm that can construct an orthonormal basis. Yeah. Every inner product space has an orthonormal basis. One can obtain an orthonormal basis from an arbitrary basis using the Gram-Schmidt process. Um, If B equals E1 through En is an orthonormal basis for an inner product space, then V is this. Let me write out exactly what this more advanced math book, how it describes the same exact algorithm, this same exact process. I want to write this out verbatim. So this is from this other book by Steinberg. This is Steinberg. Every inner product space has an orthonormal basis. One can obtain an orthonormal basis from an arbitrary basis using the Gram-Schmidt process. He quotes some other book, Book 4, Theorem 15.9, which I'm not going to look up. If B equals E1 through En, so he uses EI to mean orthonormal basis. So I will start doing the same thing. But he also used capital B for this basis of an orthonormal basis. If B equals that set is an orthonormal basis for an inner product space V, and we have a vector in our inner product space, then our vector in an inner product space is the inner product of that vector with each basis vector times each basis vector. Okay. Well, this is nice. This is a nice theorem. So now he says, in other words, the coordinate vector relative to that basis of the vector V is the inner product of the vector with every basis vector. So, in particular, if our inner product is the dot product, then this would be B dot E1 dot V dot En. But the dot product is just one form of an inner product. So, That's good to know. And then there we go. There's a little bit about the Gram-Schmidt process. And he's got a cool example of functions defining an inner product on functions that I will understand later. So, thanks for hanging out with me, y'all. Thanks for hanging out while I practice. Anybody still out there? I feel like I lost everybody. Awesome. Thanks for hanging out with me still, Ta. Appreciate it. All right, now orthogonal matrices. If A and D are square matrices, D is diagonal, and AD is orthogonal, then by definition of orthogonality, this is the definition of orthogonality. So the inverse of AD equals the transpose of AD. And, well, the inverse of a product of matrices is the inverse of the second times the inverse of the first. So those two are equal. And likewise, we have a similar fact about the transpose, that this is equal to D transpose A transpose. So now those two are equal. So you can multiply both sides of this equation by D, and then we get A inverse equals D dt AT. And D is diagonal. In a diagonal matrix always equals its transpose. So D transpose equals D, so this is D squared AT. So that is a really nice, simple calculation to find the inverse of a matrix. So on this problem, find the inverse by first finding D so that AD has column vectors of length 1, and then applying our formula. Neat. Okay, so this problem is going to be a little tougher. I don't know exactly how to tackle this one. This one is going to require a little more brain power. So, we want D equal to, I'll say D1, D2, such that well, we want AD not to just have column vectors of length 1, but we want AD to be orthogonal, right? Then AD equals 1, 3, negative 1, 3 times some number and some other number. Well, this would be D1, D2, negative D1, and 3D2. Oh, wait. Whoops. Okay, so now, yo, I hate gravity, but you love calculus. Well, sorry. That's why calculus exists. It's because of gravity, right? Okay, so D1, 3D2, negative D1, 3D2. We want the vector D1, negative D1, dot product with itself. We want the length of this to be 1, right? And likewise for the other, 3D2, 3D2, dot product with 3D2, 3D2 equal 1. So, here we have 2D1 squared equals 1, which implies that D1 is 1 over root 2. 1 over root 2, or square root of 2 over 2, whatever you want to call it. Likewise over here, we'd have 9 times D2, 9 times 2D2 squared equals 1. Therefore, D2 is 1 over square root of 18, which is 1 over 3 root 2. Right? 9, 2, yeah. So, there we go. Hey, what's up, Locky Gaming LP? How's it going? Welcome to my practice stream. Welcome to my practice stream, everybody. Is this your first time here? Locky? I think it is, right? Okay, so we found D1, D2. And it is true that D1 and D2 will be orthogonal. So did this work? Did I do this right? I would love to roll a D1. I'm so bricked up that I will learn all this in college for astrophysics. Yeah, you probably do need this for astrophysics. I've never studied astrophysics, but that sounds like this sounds like the kind of thing that you'll need there. For sure. Okay. Alright. So, pretty sure that I got all that right. How do I confirm? How do I confirm this? Yeah. Yep. I've convinced myself that that is indeed correct. All right. Then, by this little note, then AD is orthogonal. So we found a diagonal matrix such that AD is orthogonal. Then AD is orthogonal. So AD inverse equals AD transpose. I just want to get another practice rep here, remembering this derivation. So the left-hand side can be rewritten as D inverse A inverse. The right-hand side can be rewritten as D transpose A transpose. Then this implies A inverse equals D transpose A transpose. And then, therefore, because the transpose of a diagonal matrix is itself, then A inverse is D squared A transpose. So now this is D1 squared D2 squared times A transpose, which is 1, 3... negative 1, 3. Right? And this would be D1 squared, 3D1 squared, negative... Oh, wait. D1 squared, 3D2 squared. Negative D1 squared, and 3D2 squared. Okay, so I got something a little... Did I do this matrix calculation wrong? D1... No, okay, wait. Oh, if you multiply by the diagonal matrix on the right, then D1 multiplies the column. The column vectors are multiplied by D1. But if the diagonal matrix is on the left, then you multiply the rows by those diagonal entries. Okay, so that's the difference. I was like, this didn't match the pattern from before. Okay, and now recall that D1 is 1 over 3 root 2. Oh, no, this was D2. And D1, I'm pretty sure, was 1 over root 2. So, A inverse would be 1/2, negative 1/2, and then 1/2. Oh, wait, no. 1 over 6, right? 9, yeah. 1 over 3, yeah. 1 over 6, and, again, 1/6. Did this work? Let's test. A transpose, 1, 3, negative 1, 3, right? Was that the correct? Yeah. 1, 3, negative 1, 3 times, not A transpose, but A inverse here. 1/2, negative 1/2, 1/6, and 1/6. Multiplying these together, we should get the identity matrix. So 1/2 plus 3/6 is 1. Negative 1/2 plus 1/2 is 0. Negative 1/2 plus 1/2 is 0. And 1/2 plus 1/2 is 1. Yeah, it worked. It worked. I mean, matrices explain the universe. Yeah, matrices are incredibly useful. One might argue that the entire world is just a matrix. That we might live in the matrix, right? So even Schrodinger used matrices for deriving his equation. Totally. Yeah, matrices are very, very, very useful in quantum mechanics. Linear algebra is like the most useful math that there is, dude. Cool. Oh, your JEE advanced exam is in 20 days. Damn, dude. Kinetic football. I hope that it goes well. Yeah, the cat is cute. Luna is adorable, isn't she? Um. Hey, Paulo. Greetings from the U.S. Nice to meet you, Paulo. And Locky Gaming. Oh, it is your first time. The stream was suggested on the main page, and you're studying linear algebra in university. Let's go, dude. Let's go. So I've been studying this book in rotation. So I've done chapter 1, then chapter 2, then chapter 3, all the way up to chapter 10, and now we reset. And I'm doing 1, 2, 3, all the way up to 10, and then I reset, etc., etc. Okay. If I had to, you're saying if I had to pick between math and guitar, I'd probably pick math because you can make more money with math than guitar. Guitar has like zero money involved in it. Guitar is the worst idea ever. Now, different question. If I didn't have to make money, I don't know. Hard question. I guess for the last so many years I've picked guitar, but I would like to get to the point where I would pick math. Like, the higher brain version of myself would say it's a pure tie and I couldn't pick between them. But historically, I've been prioritizing guitar as a hobby for the last so many years. Yeah, dude, it would be cool to teach both music and math. That's why I'm here on YouTube. Email me. If I could find some private students who wanted me as their teacher, not just for math, not just for guitar, but math and guitar, and programming if you want, if you really want. jcpractices at gmail.com. I can teach. It would be amazing if I could be a private tutor and make a living as a private teacher, or teach both in school, and teach the connections between math and guitar or math and music. That would be amazing. I do have a guitar channel, Kinetic Football Dev. Yes. With a guitar, the best choice, your best option is smoking weed in the streets and making no money at all and becoming a loser guitarist. Yeah, that's about your only option if you pursue that. Yeah, I mean, I might show up next year for guitar while being in university. You should, dude. You should. All right, so we've solved this problem to find A inverse. Now, that was a giant waste of time because we could also, for a 2x2 matrix, we have a nice formula that this is 1 over the determinant of your matrix times, you swap the top left and bottom right entries, and then you take negative values of the other corners. Does this work as well? The determinant of this matrix would be 3 plus 3 is 1/6. Swapping the elements, we have 3, 1, negative 3, positive 1. So this is way faster, dude. Why did we just waste all our time? Don't I have better things to do with my life right now? I think that we got the same matrix. 1, 1, negative 1/2, negative 1/2, 1/6, 1/6. So we got the same matrix. It just took us a lot longer. Now, of course, this approach works much nicer for 3x3 matrices and larger matrices, whereas we don't have a nice little magical closed form solution, at least not one that's so nice and easy to remember for 3x3 or 4x4 matrices. Neuralize late today. Yeah, I was streaming classical guitar on my first channel. I'd like to swap them back and forth. Am I studying math for the love of learning, or do I have a goal? Bit of both. I do want to learn this math for myself, and I have studied math as a hobby for myself, privately for a long time. But I also now want to teach high school math. So I'm trying to get some experience teaching and thinking out loud as I solve math problems and try to explain concepts. But I'm not going to be able to teach at the college level. I'm never going to teach linear algebra, probably not. And I'm definitely never going to teach at college representation theory. Like, I'm never going to teach representation theory, but I want to study graduate level, advanced, abstract, pure math as a hobby for myself. So a bit of both. I want to teach calculus and algebra and everything to high schoolers for money. But then I also want to learn graduate level math for myself as a hobby. So yeah, a bit of both. Gotta go. It's late. Thanks for stopping by, Neuralized. Great to see you. Oh, hey, Paolo's a teacher. Let's go. 53-year-old teacher. And you've always loved math. You've had several guitars, but never learned how to play properly. Keep up the good work. Thank you. Thank you so much. If you're curious about my guitar, I do have a secondary channel where I practice classical guitar live. So here's a link to that if anybody's curious about the guitar channel. It's the same thing as this. I practice and I do my regular practice sessions and share it online and try to build community and talk about classical guitar and math. And I'm a nerd. I'm a giant nerd. So, all right, let's keep going. Next problem. That was section 6.3. Now we're going to do a problem about the projection matrix. I don't even know if I want to learn a problem about the method of least squares. It's super boring, kind of. Yeah, thank you, Locky Gaming. Yeah, I don't know. It's kind of a hard pivot to go from tech and like making a lot of money as a software engineer. Like, I worked at Google, I worked at Apple, and now I'm trying to teach math, and so I'm taking a huge pay cut to do that. But then on top of that, I have to get a lot of training. I have to like get a license and everything in order to make that pivot. So it's kind of a difficult transition. But I hope I can do it because I really like freaking teaching. So let's go to 6.4 on the projection matrix. All right, so this says, let's write it out. find the projection matrix for the given subspace and find the projection of the indicated vector on the subspace. Yeah. Kinetic Football Dev, great to see you, man. Thank you for stopping by. So we have, we're interested in the projection of 2, -1, 3 on the span of two vectors, 2, 1, 1, and -1, 2, 1. Which is clearly a subset of R3. Okay. I don't remember the formula for a projection matrix. I have to look this up. I don't remember this one. Okay, how can I reconstruct the idea here? Yeah, thanks. That's what my heart desires. Perhaps it's a step toward the right direction. Thank you, dude. Thank you. I think that we start with a diagonalization of a matrix. No, is that it? Or do we start with an orthogonal matrix? Okay, so let W be the span of two vectors. Then W also equals the span of an orthonormal basis. This is by Graham-Schmidt, right? Then the matrix that the orthogonal matrix with those basis vectors, the matrix with those basis vectors as column vectors is orthogonal. So A inverse equals A transpose. I know that this is very related. do we also use some sort of similarity, like diagonalization similarity thing? I don't. I think I'm kind of stuck. How do I get the projection matrix? I have to review. How does this work? Prashant, hell yeah, let's work on that problem. Let's make some money. What's up, Prashant? I'm chilling, dude. I'm just chilling and practicing some math. I don't remember. I don't feel like I understand the projection matrix very well. So I want to work. I want to read through this section today. Yeah, I want to. I want to. No, I don't know. I cannot solve your problem. I'm sorry. Okay. So this isn't quite enough. What I wrote is true, but it isn't quite enough. We let's write this out. The projection I find this to just be kind of a crazy formula thing that's hard for me to memorize. So I need to work through the section and try to understand the theory for why this is the formula for it. Um, Let W be the span of A1 through AK. Be a k-dimensional subspace of Rn, and let A have as columns the vectors A1 through AK. The projection matrix for the subspace W P equals A transpose A inverse A transpose. Okay, so I need to understand how we get that. And this is theorem 6.11 as well. Like, pretty much just rewrites this. Characterization of projection matrices. Projection matrix P for subspace W is both idempotent and symmetric. Conversely, every n by n matrix that is both idempotent and symmetric is a projection matrix. So, idempotent and symmetric is equivalent to projection matrix. What is idempotent? Any matrix where A squared equals A. Symmetric means that A transpose equals A. And projection matrix is a matrix that can be written as A transpose A inverse A transpose. How in the world am I ever going to memorize that? Would it help me at all to try to think of this as A inverse A transpose inverse A transpose? I don't think so. And this is confusing because this is the matrix A is not necessarily square. So A inverse does not necessarily exist. A is not a square matrix in general in this. So that's good to know. That's important. So here, I want to lose the matrix A and write P because A is, the matrix A is different than in the two different equations or portions of this math fact, this equivalence, this characterization. Okay. So knowing this, we can we can use that formula to find the projection matrix and then find the projection of that vector. So A is the matrix with these column vectors. So P is A transpose A inverse A transpose. Yeah, that's it, isn't it? A transpose A quantity inverse A transpose. I got that. So our projection matrix is the product of these matrices. And we just do a bunch of calculations. So this 2, 3, 4, negative 2, 0, 1, negative 2, 0, 1, 1, 5, 6. The inverse of that times 2, 1, 1, negative 1, 2, 1. And the inverse of that matrix would be the determinant. Times the 2 by 2 formed by swapping the top left, bottom right corners and negating the other two corners. Here, 6, 7, 6, 7. Six, 4. 6, 5. Negative 2, negative 6. Negative 1, 7. Negative 1 is 3. Now here we have, what's up? 6, 7. Yes, yes, indeed, indeed. 6, 7 came up yesterday while I was tutoring somebody. It's always a fun time. 14, 20. 8, 1. 10, 7. 7, -5. 4, 19. 5, 11. 7, 1. 4, 11. 8. So I think that this is our projection matrix P. I'm going to keep that factor factored out because why wouldn't we? Yeah, 23 is prime, so it doesn't really benefit us at all to factor 23 into that matrix. Thus, the projection of 2, -1, 3 on our space W is P. For some reason, we're using B in places in the. I'm going to use V. V seems to make way more sense to me. PV is 1 over 23. Let's just copy. Let's copy that whole matrix. Times the column vector 2, -1, 3. Uh, 2019 plus 21 is 40. -10, -29, -29 plus 33 is 4. 2, -9, 24 minus 9 is 15. And I think that this is our projection of that vector onto that basis. So let's find out. This is an odd problem, so I can look in the back of the book. I'm a little afraid. I feel like there were a lot of opportunities for mental math errors in that one. So 6, 4. Ooh, wait. 6, 4. I got a different matrix. Is it number 3? My book is actually falling apart. My book is actually in pieces now. Okay, I think I got it wrong. Let's try this again. Are we in 6.4? Was that problem 3? That was problem number 3. Alright, what went wrong? I got a different matrix. Okay, so I didn't get the projection matrix correct, so everything is incorrect after that. Let's see. Let's try again. Did I copy the wrong problem or something? Did I copy down a number incorrectly? 2, -1, 3 on 2, 1, 1, -1, 2, 1. Okay, so I copy the right numbers here. Take 2. Take two. Let's see what happened. This is kind of like take three, actually. Because the first time around, I didn't know. I couldn't remember how to build the projection matrix. So let's try again. Aha. Okay, so A transpose. I got something incorrect in this top left. I remember that these two did not match, and it made me pause for a second. I was like, I feel like A transpose A should be symmetric. This time, A transpose A is symmetric, and therefore I remember I had something different before. So that would break. I don't know. It was just a matrix multiplication problem of A transpose A. So then A transpose A is going to be 1 over 35 times 6, 6, negative 1, negative 1. All right? And so P is A transpose A inverse A transpose multiplying the rightmost two matrices, we have 12, 13, 6, 4, 6, 5, -2, -8, -1, 10, -1, 5. And now these multiplied together. 26 plus 8 is 34. 8 minus 10. 10, 5. 13 minus 16. 4, 24. 5 plus 10. 13 minus 8. 4 plus 10. And 5 plus 5. And now I think that I have the right projection matrix. So PV is let's copy all of it. And our initial vector v is 2, -1, 3. Let's give ourselves a little more room. Uh, 68, 70, 85. -6, -30, +5. Wait, no, -30, +15. 10, -4. -4 plus 30 is 26. And I think we're done. We don't have any common divisors across all of those, so let's just leave it factored, I feel, or we could distribute. 85 divided by 35 would be 17. (17/7). 15 over 35 would be 3/7. And 26 over 35 is 26/35. I think that the previous form is a little simpler, but either way, let's find out what is in the back of the book. Chapter 6, 1 over 35, 86, 13, 26. I was damn close. The projection matrix. What the hell? 34, -2, -3, 5, -3, 24. There's just some error somewhere along the way. Oh, okay, there's a smaller calculation error somewhere, but I was super damn close. So this is a -3 instead of -2. -3, 20, this is a 26. 15, 5. This one is 15. So there's literally just a mental math error in the second column. of one of these previous matrix calculations. Dang it! I need to be able to, if I want to become a professional mathematician, I need to be able to multiply matrices by hand in my head without any aid from a computer. So we're super, super, super close. Took multiple tries, but we're almost there. I want to, you know what? Good enough. Let's not waste any more time. We definitely got the basic benefit out of that problem. And my book is completely freaking wrecked. Completely destroyed this book. Now, I want to try to understand why the projection matrix is built like that. Why does it act like that? Why is it like that? Where was my mental math mistake? Doing arithmetic on camera live for the internet, it adds some extra challenges. Oh well, that's fine. There's number 3. Solve that. Oh, let's understand why. Why do we get the projection matrix like that? So I'm gonna read the section. I'm gonna eat a little bit of food while I do that. And while we do this, let's listen to some classical guitar. Hope you all enjoy this. Hmm. Sometimes you feel organic chemistry is harder than math. Organic chemistry is super hard, man. I don't think I'd be able to do very well in that class. I never actually took organic chemistry. No, I'm not gonna do JEE math. Sorry. I'm studying linear algebra. Someday, maybe, but okay. I think I more or less get it. This step is important. Why is it invertible? A has rank K, which implies that A transpose A This is a theorem that we need. Since it has rank K and it's and A transpose A is a K by K matrix. So if you have a K dimensional square matrix and its rank is K, then the matrix is invertible. 3 Mizzy, this has been a long stream. Dude, you don't even know, because I practiced guitar for like 3 hours before I started this stream. I practiced guitar on the guitar channel for 3 hours before I started here. Crazy. What am I doing with my life? Like, are you all enjoying this? Like, this feels like a terrible idea. What am I doing here on YouTube? Why am I wasting all of my time here on YouTube? Man. At least we got a few subs. We're at 1113 today. Let's go. Let's go. So, yes. Yeah, I've been practicing a lot today. I did like 3 hours of guitar, and now we're at an hour and a half, more than an hour and a half of math. Wild. Okay, so I think I follow now a bit more of how we build the projection matrix. Let's try this again. This time I'm going to build it from scratch. And let's try to do it from memory. And let's see if I can get this. So, show that P equals, the projection matrix is A transpose A inverse A transpose. What does that even mean? We want to find a matrix P such that, what is it, the projection matrix? PV is the projection of V on W for any V in, are we assuming real numbers? And W being the span of K vectors. I don't know if we assume real numbers anywhere in this theorem. Let A be a matrix with column vectors, with the basis vectors as columns, So W is the column space of A. Then any vector in W is equal to AX. I believe that the book uses AR for some R, for some column vector R. Or AX? I would use X here for some X. Because P is in the space, in the subspace, we need the dot product of any vector in the subspace times something that's in the orthogonal space to equal 0. We want, so this is some vector in the subspace, and then this I want to be in the orthogonal complement. This is P minus V. But that doesn't feel right. Oh. V minus, this would be V minus projection. And this can be rewritten as V minus a R equals 0. Then by properties of the transpose, we have X transpose A transpose times V minus A R equals 0. Therefore, X transpose times A transpose V minus A transpose A R equals 0. And this is true for all X in Rn, or in the probably in the vector space V. I don't know if all this works in an arbitrary vector space or not. I imagine. This implies that this is only true if ATV minus A transpose AR equals 0. This implies A transpose V equals A transpose AR. And this implies A transpose A inverse A transpose V equals R. And this needs a justification. A transpose A inverse exists because A is a K by K matrix. Oh wait, no, A has rank K. A transpose A is a K by K matrix, and rank of A transpose A equals rank of A by a theorem. Therefore, it's invertible, because the rank equals the size of the square matrix. Yeah. So now, therefore, P equals AR. We take that matrix as the projection matrix to project any vector V onto the subspace W. Yeah. Equals PV as desired. Okay. Now maybe I'll be able to remember that next time when we come back to this in like 2 weeks. Who knows? Probably not. Probably not going to remember it. But hey, I definitely learned a bit more. I just reconstructed the proof from memory just now, and whether or not we remember that next time, I think I'll be able to reconstruct this quicker each time. So P is A transpose A inverse A transpose. P is A transpose A inverse A transpose. We'll see. We'll see if I can remember that next time. Thank you everybody for watching. This has been a very long day of streaming. I was practicing classical guitar before we started here, and now we've just done almost 2 hours of mathematics live. Let's go. Let's go. I hope you all enjoyed this. If anybody is ever watching the VOD until now, dude, this is your chance for bragging rights. Like, brag about it down in the comment section below, and let me know that you watched all the way through this insanely long math practice stream. So, thanks for watching. I'm gonna go now. Bye. Bye, everyone. Who cares about method of least squares? We got to the projection matrix. That's the most important thing. See you, JC. Been a lovely stream. Yeah, dude. Thanks, man. Thanks for hanging out with me for so long today. I'm glad that you enjoyed it. Take care. Bye. Bye.